Hey guys, welcome back to CMTEQ channel. In this tutorial, we're going to complete our power flow analysis by drawing out first the layout of all the non-bus system, because we know that based on tutorial 1, we have to design a non-bus systems, and we already have all the ingredients that will make up this infrastructure. So to get things going, the first thing we're going to start pulling the bus bar to get the layout correct, because remember, if you get a layout correct for your network, then the rest of the things are just going to start falling in places. Right now, I'm going to go ahead and bring in all my non-bus bar onto my working space. 2, 3, 4, 5, 6, 7, 8, and 9. Right, so I've got all my non-bus bar onto my working space. So the next thing here is to basically just rename and restructures my bus bars. Now the next thing here is to basically enter the bus bar voltage information that we've got from our design. So we know that bus 1 got a 20 kilovolt because it's coming from a slack generator, and the second bus bar is got the 18, the third one is 13.8, and all the rest of the bus bar, which are basically going to be like our transmission line bus bars, they're going to be 230 kilovolt. So to set up your bus bar voltage, let's go ahead and click the bus bar and click on substation. So there is many ways to do this, and we're going to give it a short name, bus 1. Okay, the nominal voltage is 20 kilovolt for bus bar 1, the slack bus. Yes, move to bus bar number 2. And on bus bar number 2, we set it also the name as bus 2. Right, the voltage here, we know that it's 18 kilovolt. Okay, yes, we move to bus bar 3, and bus bar 3, also the short name is going to be just bus 3, and the nominal voltage here is 13.8 kilovolt. Now, all the rest of these bus bars, we know they are transmission bus bar. In between our network, they're going to all have 230 kilovolt. Right, we almost there, we almost getting there. So the next thing on our system is to complete the transmission lines parameters. Now let's bring into our problem statement here, or our network ingredients. So we know that we've got impedances right on these overhead lines. So that is a line that moved from bus bar 4 to bus bar 5. It's got this impedance of 5.23 ohm, and the reactance is 44.975. Now, this is important to note that we are using only the minimum of parameters. Remember, DigSilent is very powerful, and there are plenty of information that you can pass in to ensure that your analysis have some degrees of accuracies. But for simplicity here, we're just going to input the resistance and the reactance parameters of our cable. So the first connection is going to be on line 4 to 5. So I'm going to go ahead and pick up my overhead line here and find the cubic in which I want to connect. So let's move to cubic 1, and we're also going to find cubic 1 on bus bar 5. Then we complete this connection. Right, so before we input the line parameters, let's go ahead and finish off all the overhead line connections. So I'm going to bring in the overhead line for line 4 to 6. Okay, so let's move to cubic 2 here, and on bus bar 6 we're going to move to cubic 1. Right, so the next one is line 5 to 7. So this is our bus bar 5, so we're going to go ahead from 5 and we take cubic 2, and we're going to go to bus bar 7, and on that bus bar we're just going to take cubic 1. Great. So the next line is line 6 to line 9. So we're going to click on bus bar 6, we take cubic 2 connection, and we're going to bring it to the cubic 1 of bus bar 9. Great, so the connection is done there. Now what is our next line? So that is line 7 to 8. Where is line 7? This is line 7, so you basically must connect this way. So I'm going to click on that bus bar, cubic 2, and I'm going to this bus bar here, bus bar 8, and I'm going to take cubic 1. Right, so that connection is done. The next connection is we're going to go from 8 to 7, or from 7 to 8. And the next line, or the last line in this setup, is going to be line 8 to 9. So that will go from bus bar 8 to bus bar 9. So I'm going to click on bus bar 8, cubic 2. Then I'm going to move to bus bar number 9 and cubic 2. Great. Now we basically have all the line connected. Now the next thing here, you can clearly see that we need to connect the transformers from our bus bars and the generators, and lastly we're going to finish off by connecting the loads on the specific bus bar. As we can see here, we got loads here only on bus bar 5, bus bar 6, and bus bar 8. The rest of the bus bar, they don't have loads connected to it. They basically open for loads to be connected, basically if you are expanding your network. Right, so the next important stage here on our network configuration is to basically enter the line parameters, because you now have all your line connected. So you've got your resistance and your reactance that make up the impedance of the cable. So when you come in first, the first line is line 4 to 5, double click on the line. Okay, so it's going to bring up this page. If you've got the length of the line, the distance in kilometers or miles, whatever your case may be, you enter it there and you move on to create a new line type. Okay, so new line type, you can basically name it here 4 to 5. Then your rated voltage is 230 kilovolt. Now your amp, your rated amp, 1 kiloamp is between ground and the line is good enough. If you're going to basically be drawing more than 1 kiloamps at 230 kilovolt, you can just imagine the line losses. Okay, so 1 kiloamp should be enough. You change it to overhead line and you enter your resistance at 20 degree ambient, and that is for me is 5,293. the reactance is 44.975. okay, if you then you can leave all the rest of the parameters as is. On the load flow here, they give you some other parameters that you can play around with if you have them in hand. Otherwise, you leave everything as is and you click OK. And you can rename it here as well, line 4 to 5. Okay, just to make sure that the illustrations is indeed correct. Then you move on to the next line, so that is 4 to 6. Right, line 4 to 6. And you're going to create a new line type, also 4 to 6. Your rated voltage is 230. You change it to overhead line. Your resistance is 8,994. And the reactance for this line is 48.668. Okay and okay. Then we move on to the next line, so that is 5 to 7. Line 5, 7. New line type 230. Overhead line. The resistance for 5 to 7 is 16.93. The reactance is 85.165. The line type 5 to 7. Okay and okay. Then you can move on from line 6 to line 9, which is the next one here. Okay, so you got line 6 to line 9. You create a new line type. The rated voltage 230. 6 to 9. Overhead line. The resistance is 20.63 and the reactance is 89.936. And okay. Then we move on to line 7 to 8. Line 7 to 8, new line type 230 kilovolt, 7 to 8. Overhead, the resistance 4.489. The reactance here is 38.088. Okay, then the last line from line 8 to line 9. So you got 8 to 9, a new line type. You're rated 230 kilovolt. You got 8 to 9 overhead line. Your resistance is 6.259. The reactance is 53.326. And you said, okay. So now you've got all the line parameters in place. If you haven't missed anything, your line should be ready to operate. Right, but right now this transmission line is basically useless. Why? Because it's not transmitting anything. We just have a network lying there, long distances of overhead lines just lying there without transmitting anything. So the thing that is missing here is to connect the generating power station onto the outer bus bar 1, bus bar 2, and bus bar 3. Then we can start the process of basically transmitting power from all these power stations onto the endpoint where our consumers are located. So having said that, let me now bring in the generators parameters here as discussed on part 1 of this tutorial. So the first one on the list is the grid or the slack bus generator with a capacity of 250 MVA. Now the real and reactive power are still unknown to us. Now if you're not too sure about this question mark, please watch part 1 of this tutorial where we discuss them. Now this is a swing bus generator, so it will basically set a reference for everything for us. So now these real and reactive power are still unknown. They will basically be set based on the demand on your network. Then it is followed by generator 1 and generator 2, which are the PV bus generators. Now they are PV power controlled because we already set the maximum active power that must be drawn out of these two generators here. As you can see, we got 163 and 85 respectively from Gen 1 and Gen 2. These are very crucial parameters for us to complete this load flow analysis. So I'm going to go ahead and bring in my generators into my system. Now when it comes to generators here, you basically have two options here. You can either bring in the synchronous machine here, or you can select an external grid here. Now let's just have a look at the external grid. So if we click on our bus bar 1 here, and where is it now? So let's flip it at the bus bar. Great, so that it can be flipped up here. Now if we double click on this, we're going to see the option that we have here. Now if we select this as a slack bus generators, then we can set the voltage here 0.4 and we leave the reference angle as 0. Okay, now the terminal that we are connected, we know that we are connected on bus 1, so we leave everything as is and we can carry on with the rest of the generators. Now if you want to use the synchronous machine, okay, let's go ahead and remove the external grid and make use of the synchronous machine. So if we select a synchronous machine and we come onto our bus bar 1, again we go to cubic 1. Great, it is connected. So I'm going to flip it again at the bus bar Then let's go ahead and double click on our synchronous machine here. Now, as you can see here, you can also set your synchronous machine as a reference machine. Basically, it's going to turn to SL for slack bus. Now, you've got two options here, either power factor control or voltage control. So when we click on voltage control, you have to change the voltage here to 0.4. Now remember, our per unit voltage for the generator, slack bus generator, is 1.04 per unit. Right, so you've got other parameters here. Your angle, you're going to leave it at 0 degree because it is a reference generator. Now the reactive and real power here are also going to be left at 0 because it will be set based on the demand, as we already discussed. Then you come here on the basics here. Now here you've got the option to create a new type, and this will give you the option to basically set your maximum capacity of your generator and the nominal voltage, which is 20 kilovolt in our case, and also set up the power factor. Then you click on OK and OK. Then you basically have your synchronous generator or synchronous machine set up. If you need to, now this one got more parameters to be set compared to using the external grid. So let's go ahead and bring in the synchronous machine on the cubic one here. Okay, and we're going to flip these onto the other side of the bus bar and bring in the second one. We've got plenty of cubic here, so we go to cubic one. That's it, and that one is already flipped on the correct side. Now, as per our load flow analysis, we know that this generator 2, it is a PV bus generator. So we're going to change it to voltage control. Why? Because we're working on assumption that the voltage at this bus bar is going to be at 1 volt per unit. So it is just an assumption, so we change it to a PV bus. Now we could also leave it to a PQ, that is power, active power, and reactive power is also known to us, since we know that this particular generator has a maximum active power of 85 that must flow out of it, and there is a reactive power of -12. Now, the maximum apparent power, so that is your MVA, is only going to amount to 130 megavolt ampere. So we can basically enter those values. So that is 85 megawatt and -12 megawatt. So it is a PV bus generator, and we've got a 1 volt per unit, and we can basically say okay. And the next thing is to go to the basics and create a new type so that we can basically enter our capacity rating. So that is 130 MVA for that generator, and the nominal voltage for this generator is 18 kilovolt at the 0.85 power factor. So we can basically rename these to Gen 2, and then we're gonna say okay. Let's rename this also to Gen 2, and we say okay. Right, now we move into the next one here, that is generator 1. Okay, that is connected to bus bar 2. Now this generator 1 is also a PV generator, so let's first rename it to Gen 1 and create a new type here. We're going to give the maximum power out of that generator will be 192 MVA. Then the nominal voltage is 13.8 kilovolt at 0.85 power factor. Then our load flow variables here is also a PV, and the voltage is a 1 volt per unit as an assumption, and we don't know how much the voltage is going to drop based on the power that will be drawn out of this generator. This is why we are doing this load flow analysis. So I'm going to enter the active power is 163 megawatt, and the reactive power is 8 megavolt reactive. Then we say okay, and now we've got all the parameters for that generator. We forgot to basically just rename one aspect of it, so let's go ahead and rename that here. So we're gonna just say Gen 1 as well. Great. Now we've got generator 1, generator 2, and we've got the synchronous machine here, which is basically our grid. I'm going to rename it to the grid, and here also the grid. Now you can choose whatever name you want to rename this, and that is up to you. Great, so we're basically getting closer and closer to completing this network infrastructure here. So the next thing that is missing here is to connect the transformers, because now we're generating here at 13.8 kilovolt and we're generating on this side at 18 kilovolt. Now our external grid, or the slack bus generator here, is also generating at 20 kilovolt. Now what we need is we need transformers, because we want to get power to some remote location here. Now we cannot get that 20 or that 13 kilovolt without stepping it up, because if we transmit it at 13.8 kilovolt, that means we have to transmit it at a higher current so that we can get that whole MVA through. Now if we transmit at a higher current, remember the losses. Now if you recall, when we were entering the parameters for the line here, we said that we're going to leave the rated current for the line at 1 kiloamp, because we are assuming that since we are transmitting power at high voltage 230 kilovolt, we're going to step down the current. Okay, we're going to transmit at a lower current to reduce the power losses through the heat. Okay, so that is why now we're going to take our transformers from these relatively low voltage to high transmission line voltages. So to do that, I'm going to go ahead and pick up my 2 winding transformers, and the first one I'm going to connect it here. I've got plenty of cubic here, cubic 2, and I will connect it to bus bar 7, cubic 3. Great. And I'm going to move to the next one here on this bus bar, the slack bus. I'm going to find cubic 2 here as well. And on bus bar 4, how many cubic available? We've got 3 there. Okay, then we move on to the next one on bus bar 3, cubic 2. Then we're going to also move on to bus bar 9 and cubic 3. So we basically have transformers on all our generating bus bar. So the circuit is basically almost complete, but it will not work at this point without the correct parameters for our transformers, which I'm going to bring in here. So we got T1, T2, T3. They basically have this rated MVA. Okay, so that's a maximum power that this transformer can allow through, and the voltage ratio, as we've already spoke about them, and the short circuit parameters. Now this is important. If we're going to run the short circuit analysis on this network, we need to know how much voltage to lost through these transformers in case of a short circuit occurring somewhere on our network. Okay, so let's go ahead and enter these parameters. So I'm going to start with the slack bus or transformers here, the first one here. Now the first transformer, T1, the grid transformer or the slack bus transformer, the parameters for that transformer, MVA is 250, the ratio is 230, 20 kilovolt, and the percentage short circuit is 14.4. First, we're going to create a new transformer type, okay? And I'm going to basically name this T1. Now, the rated MVA, we say that is 250. The frequency is going to be 50 Hertz. Now, the high voltage side is the 230, because that is now going on to the transmission side, and our low voltage side is on the generating grid, that is 20 kilovolt. Now the percentage short circuit here is 14.4. Now if you want to increase the accuracy of your load flow analysis, you can come into the load flow here and add in some more parameters if you have them available. Otherwise, we're going to go to OK and OK. Great. Now we move on to the next transformer, that is T2. Now the parameters for transformer T2 are 200 MVA, 230 kilovolt and 13.8 with a short circuit percentage of 8.6. Now we may also access our transformer parameters by coming into the relevant object that we are working on and clicking on transformers. We're going to see all the description here, the 3 transformers and where they are connected. As you can see, T1 is connected to bus bar 4 on the high voltage side. That you can see here, this is a 230 kilovolt high voltage side, and on the low voltage side we got bus 1, that is where we've got a 20 kilovolt, and we can see the relevant information. The MVA here is 2 50 megavolt ampere. Now let's go ahead and click on transformer 3, and we're going to change here T3, and we're going to create a new type. Okay, we're going to name it T3. Now transformer 3 parameters are 150 MVA, 230, and the low voltage side is 18 kilovolt, right? And we've got a 12.5. Then we do not have any other information here. We're going to basically click OK. Now we move on to the last one, transformer 2. Okay, so that's T2. We create a new type. Okay, T2, that is 200 MVA, 230, and on the low voltage side here is 13.8 kilovolt with 8.6%. Now at this point here, we can basically run our load flow analysis, but the only problem here, the load flow or power flow here is only going to be calculated basically for all these transmission lines, because we do not have any load attached onto our system. So to complete this load flow analysis, we have to bring in loads on our bus bar. So we've got a load on bus bar 5, 6, and bus bar 8. So let's go ahead and locate this bus bar. So bus bar 6, 5, and bus bar 8. Okay, so I'm going to go ahead and bring in the load here. So I'm going to just bring in a general load and connect on cubic 3 of bus bar 5. Then another load on bus bar 6, also on cubic 3. Then lastly, I'm going to bring in a load on bus bar 8, also on cubic 3. Great. Now I've got all the loads set up. So now the next thing here is to basically enter the loads parameters. And the parameters for our loads are very simple, since we only have to enter the active and reactive power. So to start on bus bar 5, I'm going to double click on the general load here, and I will rename these to load 5. Okay, and I'm going to go to load flow. We don't have to create a new type here, and everything will be left at default. And I'm going to put in the active power for that load on bus bar 5 is 122 megawatt, and the reactive power is 50 MVAR. Then I'm going to click OK. Then I move to the next one on bus bar 6, right? And the load flow here, so the active power on bus bar 6, so that is going to be 93 megawatt. The reactive power is 30 MVAR. Okay, megavolt ampere reactive. Then I'm going to change also the name here. I'm going to make these as load 6. Then we click on OK. Now let's move on to the next one. So that is on bus bar 8. Great. So we're going to rename these as load 8 on bus bar 8. Okay, then on our load flow parameters, the active power value on load 8 is 105 megawatt, and the reactive power is 30 megavolt ampere reactive. And I'm going to click on OK. So that basically all I need for all my loads here. So at this point, we're basically ready to simulate or calculate a load flow analysis for our circuit. So I'm going to come on to this icon here and say calculate load flow. Then I've got options here. I'm going to choose the first one, load flow for balanced positive sequence. Why? Because that is where we were entering our parameters, right? For balanced positive sequence. So I'm going to click on execute. So if everything went right, we should be getting our simulation calculated and have all the data that we need for this network. As you can see here, we've got some problem here. Okay, let's bring in the coloring here. Now you can see that we've got an inactive bus bar, so that is the slack bus here. Okay, and the areas with red, that's obviously where there are problems. So the loading is basically showing us how the buses are loaded. Green is good for us. blue is slightly below, the voltage is below, okay? And green basically means the voltage is good, and blue it's slightly below, and if it's red, it's slightly over. And the loading also is ranging from red to orange there. Now, if we zoom into bus bar 4 here, we can see we got 1.01 per unit, and it's 233. So it's not too bad, because this bus bar is supposed to be at 230. Now it's sitting at 233, which is not that bad. And the single phase is on 234 instead of 232. Now, if you look into your lines here, we are very much transmitting the correct amount of current since our lines are not loading. But the transformers, right? This transformer is overloaded, and this transformer as well is overloaded, as well as the generator. So, and particularly bus bar 7 is very much overloaded. So we need to look into the reason why this bus bar is overloaded. Now, this is precisely the reason why we did this analysis, so that we can see where the problems are on our network. Now, here we're not even placing any load, right, on bus bar 7. The only loading on bus bar 7 is bus bar 5 is demanding, and bus bar 8 is also demanding. Now, imagine if we have to put a load here on bus bar 7, the situation is just going to get worse here, right? Because our slack bus can just do so much control. So this is where we need to readjust and make sure things are running as smooth as possible to eliminate the problem in our power system network. So I'm going to stop this tutorial here before it gets way too long. And in the next tutorial, we're going to dive deep into this load flow calculation and see where we're going to adjust our network so that we can get it into the good space. And please don't forget, if you find this tutorial useful, give it a thumbs up and subscribe to CMTEQ channel. That will be highly appreciated. Until next time, cheers.